is symmetric. Okay, it's being recorded. Yes, fine for me. Okay. So this will be equal to the energy of phi naught because H is invariant, right? So this means that even phi naught prime, so the transformed of phi naught, is a ground state. So the picture you have to keep in mind is that given one ground state phi naught, then your transformation R is walking you around all the other ground state of the system. Okay, so this is R, this would be phi naught prime, phi naught second, phi naught third, and so on. And this is R everywhere. Okay, so all Landau states are connected. So all the ground states are connected to each other by the symmetry. And so this means that whenever you have spontaneous symmetry breaking, of course, you must have degeneracy of the ground states. Okay. Now, spontaneous symmetry breaking comes into two flavors, which are very different from each other. So the first flavor is discrete spontaneous symmetry breaking, and the second flavor is continuous spontaneous symmetry breaking. Now, the second one will be the one relevant for flux. However, to start fixing ideas and understanding some basic things, we'll start describing first the discrete case of spontaneous symmetry breaking. Okay? Okay, so discrete spontaneous symmetry breaking. So let's go back to our Landau-Ginzburg Hamiltonian, but just take a scalar field. So not now a vectorial field, a scalar field. So that H will be the integral over the x 1/2 gradient phi square plus 1/2 mu square phi square plus lambda phi 4. Now phi is just a number. So this Hamiltonian is invariant under the following transformation: R of phi equal minus phi, the so-called time reversal, which is just changing the sign of the field, okay, from plus to minus, minus to plus. And of course, this is invariant. You can see that. So h of r phi, that is h of minus phi, is equal, of course, to h of phi, because you have the gradient square and every other powers is even, okay? But what about the Landau ground states here? Well, depends on the phase. So at large noise or temperature, if you want, sorry, this is noise, okay? So at large noise, when you have mu square larger than 0, then your potential will be something like that. Okay, so this is V of phi. So clearly the Landau state is phi naught equal to 0. So R of phi naught is equal to phi naught, because if you change sign to 0, you get 0. So you have that the symmetry is unbroken. However, if you have low noise, so in the order phase, when mu square is smaller than 0, okay, then the shape of the potential will be something like that, the double well, V phi, right? So this is the minus phi square part, this is the plus phi 4 part. So in this case, you have two Landau ground states, okay? So phi naught minus phi naught, and phi naught then is different from 0, right? So R of phi naught is different from phi naught. So in this case, you have spontaneous symmetry breaking. When you have spontaneous symmetry breaking, clearly it is convenient now to expand the Hamiltonian around the ground state, right? So expand around here, around any of the ground states, because the system will select one and you want to expand there. Also because in this way, we will have a positive curvature, a positive mass, and it will be much easier to treat the theory around a local minimum rather than around a local maximum, okay? So we do this expansion in this simple case. So expansion around the spontaneously symmetry broken Landau state. Okay, so by definition of Landau state, dv over d phi at phi naught will be equal to 0. And so we introduce a fluctuation. So we write phi of x as phi naught plus some fluctuating field psi, right? So psi are the fluctuations with respect to the ground state. So now you expand. So v of phi will be v of phi naught plus the gradient, the first derivative is not there by definition. So plus 1/2 psi of x squared, second derivative of v with respect to phi squared at phi naught, plus some non-Gaussian terms. Well, of course, non-Gaussian terms will be important and we'll treat them in the future. But for the moment, let's stay at the Gaussian level. So you see this number here, the second derivative, is the new mass. It's simply the new coefficient of the quadratic part, right? So we can define a mu square of psi, which is the second derivative of v with respect to phi squared at the Landau state. And now this, by definition, is positive because we're expanding around the minimum. Okay, so it's the curvature in the minimum, which by definition is positive. So in the Landau-Ginzburg case, what we have, so when v of phi is 1/2 mu square phi square plus lambda phi fourth, so then dv over d phi equal to 0 gives us mu square phi plus 4 lambda phi cube. So this gives us phi naught square equal minus mu square over 4 lambda. So this is the value of phi naught. And remember, mu square, the original mu square is negative, right? So this is positive, which is fine. And so the mass of the fluctuation, the mass of psi, right, which is again just the second derivative with respect to phi naught, sorry, to phi at the Landau minimum, will be mu square plus 12 lambda phi naught square. And if you plug in the value of phi naught, you get minus 2 mu square. Okay, so then by expanding around the minimum, you have a new mass, which is, of course, strictly related to the old mass, but with the opposite sign. So it's 2 modulus of mi squared, which is positive. So this is the new mass of the fluctuations. Now, why am I fixated so much on the concept of mass, on the coefficient of the quadratic term in the expansion of the Hamiltonian? Well, because the mass contains essential information on the correlation length of the system, at least at the Gaussian level. And remember, the correlation length is what we are really interested into at the experimental level. So what I'm going to give you now is a very brief and standard explanation of why the mass, that is the quadratic, the coefficient of the quadratic term, is connected to the correlation length, because for some of you may not be immediate if you haven't done field theory before. So let's take a small detour on mass and correlation length. Okay, so now that we have expanded the system around some local minimum, okay, it makes sense to just keep the Gaussian terms. I mean, that is an approximation, but at least it's an approximation which makes sense. As long as we were staying with a field which was phi, the original phi, so around this point, it wouldn't make any sense to just treat the system at the Gaussian level, because it would be a negative Gaussian curvature, so it would be a totally unbounded energy. While if we are around the sum of the ground state, at least it makes sense, even though it's certainly not an exact thing, it's an approximation, but it makes sense to treat the system at the Gaussian level, okay? So what we do is the Gaussian approximation that you can do only if you have a positive quadratic term. So our Gaussian Hamiltonian now of psi, which is the fluctuating field, will be 1/2. Well, the gradient goes into the gradient, of course, because it was just defined up to a constant, mu square psi, psi square. Okay, so just the Gaussian part, just the quadratic part, where this, remember now, is positive. Okay, so go to Fourier now. So let's write the same Hamiltonian, the Gaussian Hamiltonian in Fourier space. What you get is an integral over ddk, 1/2, and you have k square plus mu square of psi times psi of k, psi of minus k. To do that, we did some tricks, not particularly terrible. So we have a gradient square of psi, which by integrating by part, we wrote it as psi second derivative of psi. And then when you go to Fourier, the second derivative gives you minus k square. So this goes to an integral of k square psi square. Okay, so this was the small trick that we did. Okay, so then the distribution psi psi p of psi of k. So the distribution of the field in k space will be 1/z e to the minus integral over ddk of 1/2 psi of k, k square plus mu square plus of minus k. So it's a good old Gaussian distribution, even though this is a field. So if you now compute the 2 points correlation function, so it's basically the variance of that distribution. Well, you know that this is just the inverse of the coefficient you find up at the exponent, right? So this will be 1 over k square plus mu square of psi. And if you do the calculation carefully, you see that you also have a delta function on top, but never mind that. So this is now the correlation function in k space, right? Everything is Gaussian, and so it was a piece of cake to compute that. So let's go back to real space. So back to R space. So if you go back to R space, we have to do the Fourier transform of that. So we have the G of R, so the correlation function, which is psi of x plus R. Okay, so we have just to transform that thing. So integral over ddk of e to the I k r over k square plus mu square. Now, these things, the actual value of this integral depends on the dimension d. However, let me now skip some of the details, but let me give you the gist of that. So you do this kind of integral in with the Cauchy method. So you have to check the poles on the complex plane. So clearly you have 2 poles in the complex plane, in the radial complex plane of k, and the poles are at k equal plus minus I mu, right? So then you integrate on one of the 2 planes according to the sign of the exponential. But in both cases, you will get object of the like of e to the minus mu times r. Okay, so this comes from the exponential part. Moreover, from the power law part, you see that that integral goes like k at the d minus 2, right? So you have d powers here, and you have 2 powers here. So when you go back to the R space, it will go like 1 over R to the d minus 2, okay? So if you do that carefully in 3 dimensions, right, you get G of R up to numerical factor equal to e to the minus mu R, which comes from the integration of the in the Cauchy space, divided by R, because d minus 2 in d equal 3 is equal to R. Okay, but more in general, in generic d, so for d generic, this will always be some short range function of mu times R divided by R to the d minus 2. Okay. So this is now the correlation function in real space. So how the correlation between the fields psi decay in the real space. We want to write that has e to the minus r over some correlation length, psi. So the rate over which the correlation function decays, right? So psi is the correlation length. So then you see that at the Gaussian level, and I stress at the Gaussian level, psi is just 1 over mu. So this is why we are so obsessed with the mass in field theory, in statistical field theory, because at least at the Gaussian level, and sometimes way beyond the Gaussian level, the mass is intimately connected to the correlation length. The mass is the inverse of the correlation length. And remember, the correlation length is what we directly measure in our experiments, okay? So this is only through the Gaussian level. So the interaction, the non-Gaussian terms in the Hamiltonian can change this result and typically change this result. And this process is called renormalization. We will see a little bit of that later. However, for the moment, the only important point you have to, the message you have to take home is that the curvature, the positive curvature of the potential around the minimum is closely connected to the correlation length, which is our primary experimental observable. Okay. So, okay. So back to our discrete spontaneous symmetry breaking. So we see that, so back to discrete spontaneous symmetry breaking, we see that nothing particularly spectacular happens when you break a discrete symmetry. So when you are in the, let's say, large temperature phase above the critical temperature, you have a positive mu square, right? So in this case, then psi is 1 over mu, which is finite, right? So the curvature around here is finite. When you break the symmetry and you are below, not at the transition, but below the transition where you have broken the symmetry, then you have to expand around this point, right? So this is t smaller than tc. So mu square here is negative. However, the mu square of the fluctuation is positive. And so psi is 1 over mu of the fluctuation, and it is still finite. So if you're careful enough just to change the field, so to go fluctuating around the minimum, nothing particular spectacular happens here, right? So you go from a large temperature phase, a high temperature phase with a finite correlation length, well, down to a low temperature phase where again your correlation length is finite, is the inverse of the mass, okay? Now, what we shall see now is that for the case when you break a continuous symmetry, this scenario changes radically. Okay. Are you all still there? Giulio, are you okay? I don't have any feedback. Okay.
Yeah.
Okay.
We are all with you.
I could be talking to the wall for hours.
Yes.
I wouldn't know. Okay. Good to know that you're not a wall. Okay, so let's go now to continuous symmetry breaking. So to illustrate the case of continuous symmetry breaking, you need at least 2 or more components of the field. So instead of having a scalar component, you have to go to a vectorial field, and to keep the algebra and the drawing simple, we'll just use 2 components, even though flocks have 3 components, but it doesn't matter, okay? So we consider 2 components. So we go back to our good old ON model or vectorial Landau-Ginzburg, so which was d mu phi alpha, let me write by component now, d mu phi alpha, the gradient square, plus 1/2 mu square phi alpha plus lambda phi alpha square. Okay, so this Hamiltonian 2 is invariant under transformation, and the transformation is rotations, of course. In this case, rotations on a plane, okay? So you can rotate with a parameter theta your field phi in the usual way. So cos theta minus sine theta cos theta acting on phi 1, phi 2. So this is just SO2, which is isomorphic to U1, but never mind. So it's rotations on the plane. So you can clearly see that H is invariant under this rotation. Is what we said before. So this theory is not dictating to the flock in which direction it should fly. So we have now a symmetry, which is a continuous symmetry. Well, continuous here seems to mean that you can have a very tiny little bit of this transformation. The fact that having this continuous parameter theta allows you to just make a small transformation, which is something we couldn't do in the scalar case, right? In the discrete case. You can either change sign or you do not change sign of the field. You cannot change sign a little bit of the field. While rotation is continuous, the important point you have to understand now is just that you can do this transformation in infinitesimal amounts. And this is exactly what we will use later on with the word identities to prove something. The fact that you can do an infinitesimal transformation, that you can expand this transformation for small theta. Okay, so what about its breaking? Well, as in the discrete case, whether or not the symmetry is broken depends on the phase. So let's see that again. So now at large noise or temperature, we have mu square larger than 0, right? So in this case, the potential is something like that. It's just, okay. Well, down here will be parabolic. So clearly in this case, you have just one Landau state and the Landau state phi naught is equal to 0, right? So R of phi naught is equal to phi naught. So same thing as in discrete case. Here, in this case, the symmetry is unbroken. Okay. However, at low noise, so when mu square is negative, which is the one of interest for us, which is the case of flux, okay. Well, remember, in that case, the potential has this kind of Mexican hat shape. So this is phi 1, this is phi 2, and you have a whole line of minima down there. These are all Landau states. So the system will just select one. Okay, so down here you have, let's say, the projection of the line of minimum of the potential. So the system will just select one possible Landau state. So let's say this one here. Okay, why not? So clearly here, all these Landau states are different from 0. And so R of theta of phi naught will be another point along that line, which is different from the original point. So your transformation has rotated the Landau state to another Landau state. Okay, so you have spontaneous symmetry breaking. So from the shape of the potential, we immediately get the value of phi naught. So phi v is 1 alpha mu square phi square plus lambda phi fourth. So we did that before, but let's do that again. So 0 is the v over the phi. So mu square phi plus 4 lambda phi cube. And so what you have is that the modulus of phi naught square is minus mu square over 4 lambda. And we have to keep this for future reference because we will use the expression for phi naught over and over in the following algebra. Okay, so again we have, so if we just plot the plane phi 1 phi 2, we have a line, a circle of minima, right? All of them with the same modulus given by that equation, and the symmetry The transformation under which the Hamiltonian is symmetric walks us around this manifold of ground states. Okay. So what about the expansion? We did an expansion before around the Landau ground states. So the system will select one of these ground states. For example, the system has decided to stay here. So I don't know, here, up here, or here. So what we want to do now is an expansion around that minimum. We have to be more careful than before and will be more complicated because we have two components. Okay, so let's do this. So expansion. So let's do an expansion around the continuous spontaneity symmetry broken Landau state. God, this is a long title. Okay, so we have to express the field in terms of its fluctuations. So to do this, we have to, first of all, decide or take one arbitrary Landau state. Okay, so let's take this point on the circle as our Landau states. So the system has decided to go in that direction, right? So this is the phi naught. Okay. But in general, you will have any other value of phi, okay, because the field will be fluctuating. So this is a generic phi. Okay, so you will have fluctuations, and we divide this fluctuation into two kind of fluctuations. So the fluctuations along the value of phi naught. So along the symmetry broken state, we call them delta phi longitudinal. The fluctuations orthogonal to the spontaneously broken states, we call them delta phi perpendicular transverse, right? So what we are saying is that the axis of the Landau ground state will be the longitudinal axis, while the axis orthogonal to that will be the perpendicular or transverse axis. So we are choosing this representation, which seems natural enough, right? So you can even have fluctuation along the state that you have already selected, or fluctuation transverse to that, right? So we have the longitudinal, so we use the delta phi longitudinal and the delta phi perp perpendicular, or simply perp or transverse. Okay, so you see that our phi, okay, it will be phi naught plus delta phi. So delta phi is what I called psi before. Now I want to emphasize that it is a fluctuation, so I really call it delta phi. Okay, so along the one direction, this is simply phi naught plus the longitudinal fluctuation, while along the phi 2 direction, this coincides with the perpendicular, the transverse fluctuations. Okay, so what we're saying is that phi naught is equal to, phi 1 is equal to phi naught plus delta phi longitudinal, while phi 2 is simply equal to delta phi perp. Okay, so what we want to do now is to rewrite v of phi as a function of delta phi longitudinal and delta phi perp. Okay, exactly the same kind of expansion we did before. Okay, so v of phi is 1/2 mu square phi 1 square plus phi 2 square. This is the original definition, plus lambda phi 1 square plus phi 2 square. Okay, so now we substitute their expression in terms of the fluctuation. 1/2 mu square, and then we have phi naught plus delta phi longitudinal square plus delta phi perp square. This is the Gaussian part, plus lambda phi naught plus delta phi longitudinal square plus delta phi perp square, everything square. And remember, we will have to do this developing these squares recalling that phi naught square has its own expression, which is minus mu square over 4 lambda. And once again, mu square is negative, so this is fine. So we have to develop of these squares. This is just 5 lines of algebra. I mean, you can do that by yourself. It's really easy. I will just collect now powers, and you can check by yourself that this is actually correct. So we go on with this developing of all the powers. So what is B? So first of all, there are constants, which are irrelevant. I don't care about constants. So for example, this mu square, when it hits this phi naught square, gives a constant factors, which we don't care about. So let's go power by power. So first of all, the linear terms. So the linear terms you have mu square phi naught delta phi longitudinal plus 4 lambda phi naught cube delta phi linear. Okay, so these are the linear terms. Okay, and it would be strange to find linear terms, but as we'll see in a minute, these are actually 0. Then the quadratic terms, which are very important because they contain the masses. If you develop the powers, you have 1/2 mu square delta phi longitudinal square plus 1/2 mu square delta phi perp square plus 4 lambda, sorry, this is a lambda, phi naught square delta phi longitudinal square plus 2 lambda phi naught square, this is a square, delta phi longitudinal square plus 2 lambda phi naught square delta phi perp square. So these are all the quadratic parts. And really try and do this calculation by yourself. It's absolutely boring and easy, but it's one of those boring and easy pieces of algebra which gives such a nice and beautiful result, which is worthwhile doing. Okay, cubic terms. Cubic terms, we have 4 lambda phi naught delta phi longitudinal cube plus 4 lambda phi naught delta phi longitudinal delta phi perp square, right? So this is cubic. And finally, we have the quartic terms, lambda delta phi longitudinal fourth plus lambda delta phi perp fourth plus 2 lambda delta phi longitudinal square delta phi perp square. So this is quartic. And notice that this is the only very easy one because this is just lambda delta phi square plus delta phi perp square, which was to be expected, right? It's just the quartic terms written in this new coordinates. Okay. Now you want to use this condition here. So the actual value of phi naught, which is minus mu square over 4 lambda. Okay. So if you do that, then the linear terms, which were mu square, well, becomes mu square phi square plus 4 lambda phi naught cube, they becomes phi naught times mu square minus 4 lambda times mu square over 4 lambda and 4 lambda goes, and this is equal to 0. So fine, we don't have any linear terms. That would be very surprising given the original form of the Hamiltonian. And now we have the quadratic term. So let's start from the quadratic longitudinal term. So if you isolate the delta phi longitudinal square, then this is multiplied by 1/2 mu square minus 4 lambda mu square over 4 lambda minus, I guess it's a minus 2 lambda mu square over 4 lambda. Okay, so 4 lambda and 4 lambda goes, this lambda goes with that, this 2 goes with this 4, giving a 2. So this is minus mu square delta phi longitudinal square, okay? Which we can simply call plus modulus of mu square, because remember that mu square is negative, delta phi longitudinal square. Okay, so you see that the longitudinal fluctuations, the longitudinal field, they have a nice normal quadratic coefficient, just like in the discrete case. So let's now see the the quadratic perpendicular term, the perp term. So if you take delta phi perp square out, you have 1/2 mu square minus 2 lambda mu square over 4 lambda. Now this lambda goes with this lambda, this 2 goes with this 4, giving a 2. So this is 0. And this is an important result. As we shall see, this is the important result, and it is the most important results of today's lecture. Okay, and we will comment over that in a minute. So we do not have a quadratic perpendicular term. So the perpendicular fluctuation do not have a mass. So if we want to rewrite the Hamiltonian, we get integral over ddx of 1/2. So the gradient simply becomes the gradient of the original fields. So nothing particularly spectacular there. Plus we have 2 mu square of delta phi longitudinal square. So the longitudinal part has got a quadratic term. And then there is a non-quadratic terms. So the cubic part can be rewritten in this way: 4 lambda phi naught delta phi longitudinal square plus delta phi perp square plus lambda, the quartic term, delta phi longitudinal square, delta phi perp square. Okay, so this is the expansion of our Landau-Ginzburg Hamiltonian around one continuous symmetry broken Landau state. So we conclude the following things. So from this, 1, the Gaussian, or also say free, but let's call it the Gaussian longitudinal field is massive. It has a non-zero mass, right? In particular, mu square longitudinal, it's equal to twice the modulus of the original mass. However, the Gaussian transverse field, as we said, is massless. So m square perp, it's equal to 0. So you have transverse massless fluctuations. Right, so this is was a rather pedestrian way to obtain a very important results in theoretical physics, which is called the Nambu-Goldstone theorem. So what we have seen is really a manifestation of the Nambu-Goldstone theorem. The Nambu-Goldstone theorem is telling you that whenever a continuous symmetry is spontaneously broken, massless fields emerge in the theory. So these massless fields corresponds always to fluctuation that keep the fields on the ground state manifold. And the number of massless fields is equal to the number of generators of the symmetry. So we can summarize in this way. So continuous spontaneous symmetry breaking imply the existence of massless fields. Okay, but we know more. And these massless fields are fluctuations. Okay, keeping phi on the manifold of Landau ground state. And the number of these massless fields is equal to the number of generators of the symmetry. So in our case, this is a planar rotation. Planar rotation is just one generator, right? And so we have one massless field, and the massless field is delta phi perp. Okay. So this is a very important results in field theory, okay? And geometrically, the interpretation of this is really very easy. So geometrically, what the Goldstone theorem is telling you is simply the idea that once you select some Landau minimum in a continuous in the continuous case, then you have fluctuation which carries you, well, let's make them blue, fluctuation which carries you up and down the hill, right? And these are the delta phi longitudinal, and they cost energy, so they are massive. On the other hand, you have another kind of fluctuation that carries you around the manifold of the ground states. These are the delta phi perp, and those are massless simply because they cost no energy, because you have a continuous manifold of states, one connected to each other, and all have, by definition, the same energy. So the massless fields simply correspond to fluctuation along the line of the ground states. And it's just telling you that the second derivative, so the curvature of the potential along that line is zero, right? So the curvature along the Landau, let's say, line, it's equal to zero. So this is simply why delta phi perp doesn't have a mass, because the curvature along that is zero. And just a little bit of terminology, these massless fields are also called Goldstone mode. Okay, they are called also Goldstone bosons in particle physics, zero modes, marginal modes, but for us, we call them massless fields or Goldstone modes. Now, this is important. Why this is important? Well, we've seen that at the Gaussian level, at least, psi, the correlation length, is 1 over the mass. So this seems to imply that spontaneous symmetry breaking continuous of a continuous symmetry is giving us that the transverse correlation length, it is the correlation length of the correlation function of the transverse fluctuations, which is 1 over the transverse mass, is infinite. So scale free. And this would just be from Goldstone. So from a piece of geometry and algebra, which has certainly nothing to do with evolution or with adaptation. So this is the kind of role of theoretical physics I was mentioning at the beginning of my lecture yesterday. So we found the results, which is telling you that once you break a continuous symmetry, which from the practical point of view means once the flock has managed to select one direction of motion. So once there is polarization, okay? Once there is polarization, it's unavoidable to have a massless field. That is, it's unavoidable to have an infinite correlation length, which I remember that in finite size implies that psi perp should scale linearly with the size of the system. However, this seems to be only true perhaps at the Gaussian level, because what we've seen before was that the correlation length is the inverse of the mass when we could do the easy calculation in the Gaussian case. So is this result also true beyond the Gaussian level. So is the Goldstone theorem true at all level in the perturbation theory? So is that just a Gaussian result, a perturbative result, or is a non-perturbative result, which is always true? Well, the answer is that the Goldstone theorem is always true. It doesn't depend on whether you're at the Gaussian level or the interacting level, or what order of the perturbation theory you are. It's a non-perturbative result. And I would like to give you now at least a very brief notion of how you can prove that the Goldstone modes are just non-perturbative objects, and they are always massless, irrespective of whether you are at the Gaussian or the non-Gaussian level, which is important because it's telling us that this thing here, so the fact that psi perp is equal to infinity is always true. It doesn't depend to be only at the Gaussian level, okay? To do this, we have to see something called Ward-Takahashi identities. So let's see this very briefly. So Goldstone from Ward how was that? Hashi identities. Okay, so if the Hamiltonian is symmetric in the system under some continuous symmetry, or anyway under any symmetry, then the free energy as well will be symmetric. So let's consider the Helmholtz free energy, F, which would be a function of some external magnetic field H. So 1 minus 1 over beta n. Now I'm using heavy stat mech terminology because this is actually is a kind of heavier stat mech detour that we're taking. So 1 over beta n, beta is the inverse temperature, n is the size of the system, the log of the integral over phi, the functional integral over phi, so the integral over the phase space, of e to the minus h of phi, and we have the field conjugated to the, sorry, both are called fields. H is the external field, which you can also call source, and phi is the fluctuating field, but never mind. Okay, so H is like a magnetic field conjugated to the magnetization in a ferromagnetic system. Okay, so if you have symmetry, then this quantity here, the free energy, can also be written like integral over the phi, e to the minus, instead of h of phi, you can write h of r of phi. Because if you have a symmetry, the Hamiltonian is invariant under rotation or whatever is the transformation of phi, minus integral of h scalar product phi. So now change variable. Change variable, so you call now this guy, you call it phi tilde, okay? And so what you have, this is a rotation, you don't have to worry about the Jacobian, so logarithm of integral over d phi tilde of e to the minus h phi tilde minus, so the change of variable here gives us h, and here you have, well, the transpose transformation of phi tilde. Okay, so basically you have carried the r from inside the h into the field part, the external field part. So what is this? Apart from the change of variable, is the same as before, but with a different field. So this is F, the free energy of the rotated field. So we are getting something quite reasonable here, that if the Hamiltonian is invariant, also the free energy is invariant, but not under rotations of the internal field phi, but under rotation of the external field h. Okay, so let's go to our simple case of SO2 now, right, in which you have the two components, and we said that this was the longitudinal and this was the perpendicular part. So let's call the vectorial field H, let's call it H perpendicular, sorry, H longitudinal, H perpendicular. So then the rotated of the field is what? Well, is the good old cos theta h parallel minus sine theta h perp, and sine theta h parallel plus cos theta h perp. Now we do something that we can only do because the symmetry is continuous. That is, we expand for small theta. If this was a discrete symmetry, plus minus, there would be no way to do this expansion. If f of h is equal to f of minus h, there would be no way to make this expansion. But this is a continuous symmetry, so we expand that. So this is h parallel minus theta h perp, and this is h perp plus theta h parallel. Okay, and now again, because it's continuous, I can expand now this equation here for small theta. So continuous symmetry, I expand f. So f of h parallel h perp, it's equal to f of h parallel minus theta h perp plus theta h parallel. And now I expand it, so I get f of h parallel h perp minus theta h perp, partial derivative of f with respect to h parallel, plus theta h parallel, partial derivative of f with respect to h perp. Okay, so this goes with that, and we get this identity. H perp df over the h parallel equal to h parallel df over h perp. So this kind of equations, so equations which constrain the free energy thanks to a symmetry of the system, is what we call in field theory in general word Takahashi identities. So whenever you have a symmetry, you always can generate relations not identical to this one of their own sort, but the important point is that by using the symmetry inside the definition of your free energy or of your generating functional in general in field theory and making derivatives, you can always derive this kind of identities, okay? So the important point here for what concerns us is that, remember, had you had a discrete symmetry like f of h equal to f of minus h, then there was no way to obtain a differential equation for f. You could still get some identities, but not of the differential sort that we have here. But this is very important to have this differential equation for us. Why? Because now what we do is to derive with respect to the transverse field. So derive to the respect to h perp, and then put h perp equal to 0. Okay, so let's do this. So what we get is df over dh longitudinal plus h perp second derivative of f with respect to h perp h longitudinal equal h longitudinal second derivative of f with respect to h perp square. And now we evaluate that at 0 transverse field, so this goes, okay? And so we are left with the equation df over dh longitudinal, it's equal to h longitudinal second derivative of f with respect to h perp, which is just another way to write the same word Takahashi identity. Why this is important? Well, now it's time to recall a little bit of standard stat mech, and remember that the derivatives of the Helmholtz free energy with respect to the fields are connected to the observable of the system. In particular, the first derivative is the order parameter. The magnetization would be in the Eisenberg model, right? In the Eisenberg model. While the second derivatives are the susceptibilities, right? Connected to the fluctuation. So in this case, then, minus df over dh longitudinal is what? Is the average value of phi in the longitudinal direction. So is the longitudinal or the parameter. Okay. But given our symmetry, so given our geometry, remember, so we had some spontaneously broken state here. So we call the direction of phi naught, we call it the longitudinal one, and the perpendicular one is the perp, right? So clearly in this case, phi, the average of phi longitudinal, well, it's simply phi is the modulus of the average or the parameter, okay? Because the longitudinal direction is defined as the direction of the order parameter, okay? On the other hand, what is the second derivative? Well, minus the second derivative of f with respect to h perp square. Well, the second derivatives of the free energy with respect to the fields are the susceptibilities. So this is chi susceptibility perp. So this is the transverse susceptibility. So what we get then from this identity here, once we understand that the derivative of f are the order parameter and the susceptibility, is an equation like that. The modulus of phi, the average of phi, is equal to h longitudinal times k perp. And this not at the Gaussian level. We never computed anything in an approximated way. We simply use the symmetry, right? So notice that we haven't used the breaking of the symmetry yet, because you see, now if you have no spontaneous symmetry breaking, so if the symmetry is restored, what happens? Happens that when the field goes to zero, so as long as you have a field, it's natural to have a non-zero order parameter. But if you now let the field go into zero, and if you don't have spontaneous symmetry breaking, then what you have is that also the order parameter, the average of the field, will go to zero, right? So that equation will just give us 0 equal to 0. But now, if you do have spontaneous symmetry breaking, this means that even when you let the field go into 0, then your order parameter, the modulus of it, will stay different from 0. So you have a spontaneous order parameter even in absence of the field. And so that equation is telling us that chi perp is equal to the order parameter over h longitudinal. And this now, when h longitudinal goes to 0, because the numerator, this guy stays different from 0 because of spontaneous symmetry breaking, this goes to infinity. And this is the susceptibility. Now, if we know a little bit of susceptibility, we know that there are many relations connecting susceptibility and correlation length, in particular in general psi scales like chi to the nu over gamma, which are two critical exponents. So the bottom line is the following. If you have that chi perp is infinite, then you certainly also have that psi perp is infinite, which is Goldstone. So Goldstone modes, what we say that Goldstone modes are protected by the word identity. They're protected by the symmetry. Protected against what? Well, protected against renormalization, because normally you have that the Gaussian results, the bare results, are changed by the interaction through renormalization. But when you have a symmetry, some of the results that you get at the free level, tree level, Gaussian level, whatever you want to call it, stay true also after renormalization, thanks to the symmetry. So the symmetry is protecting the Goldstone modes, so they are massless at the Gaussian level and they stay massless. Okay, so after this long excursus, we can go back to flux. So let's make our first return to flux. Okay, so now that we have learned some field theory, in particular the consequence of spontaneous symmetry breaking in the continuous case, let's go back to our experimental result, namely the fact that flocks display scale-free correlation of the velocity fluctuations. So that the psi of the velocities as a function of L is something that scales very much linearly with L, okay? So let's still ask to ourselves, is this surprising? So more specifically, do we need any biological, bona fide biological mechanism to explain this? Well, after what we've seen up to now, the answer to this is no. It's not surprising, and we do not need any specific bona fide biological mechanism to explain this. Why is that? Well, the fluctuations delta V around, so this is the correlation length of the fluctuations delta V. So the fluctuations delta V around the symmetry broken states are just the fluctuation of the orientation of the direction of motion of birds with respect to the overall direction of the flock. So clearly you can say that in a flock, the rotational symmetry of the system is broken. Okay. Also, because the polarization is large, so alignment is large, okay, and this is very important because phi is large, so because you are close to you're deep into the low noise phase, okay, so everybody is more or less going in the same direction. So this means that compared to the overall direction of motion of the system, okay, the fluctuations delta V will be mostly transverse. So the biggest part of the fluctuations delta V are the delta V perp that we've written in our case, okay? So if this is the direction, overall direction of motion, because you are in the strongly ordered phase, basically all your fluctuations are transverse. The biggest part of the fluctuation are transverse, okay? So this means that then what you compute as the correlation function of the velocity fluctuation, it's indeed the transverse correlation function, okay? But we know from Goldstone, okay, that psi perp it's equal to infinity. So in a finite size system, psi perp scale with L. So even though we cannot prove the Goldstone theorem for flocks, because remember, we have proven the Goldstone theorem under the assumption of quasi-equilibrium. So it's actually an equilibrium result, while flocks are not really at equilibrium, not at all. Okay, that was an assumption. However, this result really stinks of Goldstone to high hell. So what we're saying is that the transverse fluctuations cost nothing. It not only cost nothing to in field theory, but it also costs nothing to birds because that is just a change of direction. So clearly a change of speed, so the longitudinal direction will cost some energy, but the transverse direction, it's natural to believe that even in this biological case, they have a zero cost. So the fact that the flock is overall all going in the same direction, so you have spontaneously broken a continuous symmetry, so you have continuous spontaneous symmetry broken, this is certainly enough to suspect that you may have some Goldstone mechanism at work such that psi of V scale with L. So again, this is not proof, but it's something which really is warning you against saying, look, I don't think you should need any biological mechanism to explain that. Because the simplest system, the simplest field theoretical system has exactly the same result, just as a virtue of a spontaneously breaking a continuous symmetry, okay? So what we conclude in this case is that your experimental result, that is the psi of v of the velocity fluctuation is scale-free, is somewhat, let's say, biologically boring. Well, I don't want to say anything stupid, but biologically boring simply means doesn't really need any specific biological tuning or adaptive mechanism to be explained. This is simply, well, not so simply, but let's say simply consequence of physics and math. Now, of course, it doesn't always happen, but once you are all flying in the same direction, so if phi is larger, and certainly there are reasons why the flock is able to polarize and go and fly in one direction, and we've seen that, the imitative dynamics and so on and so forth. I'm not saying that displaying long-range order is trivial. What I'm saying is that once you are capable biologically to break a continuous symmetry, then there is nothing else you have to do to get scale-free correlations of the velocity. That is just automatically given from you by Goldstone. So this is what I meant in the first lecture by saying that theoretical physics has somewhat the role of a sentinel. It prevents us from finding biological explanations that really are uncalled for. And this is the case. But as we shall see the next time, this is not the whole story. Remember, what we've seen today is that there is another mass, the transverse mass, and that is, sorry, the longitudinal mass. And that is different from zero. So the longitudinal correlation function, correlation length, should not be infinity. So is this the case in our data? This is what we will see. This is what we will see tomorrow. Okay, Giulio, I stop here today. I think it's quite enough.
Okay, thank you.
Questions for Andrea? Yes, well, maybe Chiara, you can ask directly.
Okay.
Yes.
This is called Larsen effect, or feedback also. Well, now I'm not hearing anything, as you certainly know. You're both muted.
All right.
Okay, good.
I'm here. So is it? Wow, fantastic. Is it the calculation you have done on the Helmholtz energy with this polar representation? Couldn't you do in the free energy as well before? Because before you use the perpendicular and parallel, and then you could not be exact at all levels because you had to expand. Couldn't you do the polar representation, so the theta?
This is the classic spoiler question. You're jumping to my next lecture. Yes, okay. Yes, you can do that. You can do that, and that is actually the correct thing to do. This is a very bad spoiler.
Sorry.
But anyway, yes, but before doing that, let me notice this. The representation perp and the longitudinal is very natural from the experimental point of view, meaning that if you really want to couple a field, an external field to your degrees of freedom, right? You do that by putting just a scalar product of magnetization times h. And once you do that, it's quite natural to decompose that as the longitudinal part of the field and the transverse part of the field. It's something that you can really do and measure if you do a perturbation response experiment, so just by putting a field now in a real experiment. The other representation, so modulus and theta, would force you to actually conjugate a field to the modulus of the other parameter. And that is something not physical. It's something very handy from the analytical point of view, but it's not something that you can do in experiment. I mean, you can do that in a simulation. You can actually talk to Julia about that. She's doing exactly that in her simulations right now. But how would you do that in an experiment? Because in an experiment, the concept of conjugated variable cannot be whatever we want in a simulation. So you have the magnetization and you have the field, or even in biology, right? If you have some, well, we don't know what is the concept of conjugated field in biology, but it's the scalar, something which aligns to some external field really calls from a scalar product, which then decomposes into longitudinal perpendicular. But the field which goes in the Hamiltonian like h rho times the integral of h rho times the modulus of the degrees of freedom is something that you cannot very easily tune in an experiment. And this is the whole trouble about this double representation, the longitudinal perp and the theta rho. And I will expand a lot about that in the next lecture.
Okay, thanks.
Thanks for the spoiler.
Yes, I think it's
Sorry.
better if you use a question here. Oh, come here, so it's easier. Just the chair for the question. Oh. Hello.
Hi.
I was wondering, how do bird flocks behave in strong wind? And that would be something like an applied field that breaks the symmetry.
Yeah. It would be great to know. So what the gentleman is saying is, so you're kind of assuming that there is spontaneous symmetry breaking, right? However, sometimes it could be non-spontaneous symmetry breaking, like they're going on in the same direction because there is strong wind, or which is actually much more frequent because you have a predator arriving from one side, and so they now all go on the other side. So it would then mean that if I measure the correlation length in that case, I should not find the scale-free behavior. Now, that would be lovely. However, remember, these are real data, real experiments. So we are lucky that we can get enough data on free flying flocks, and we have about, I don't know, 12, 15 points in our plots. When there is strong predation, we cannot get the data because they get too dense. If there is strong wind, they just do not flock over their roost. And it's not only that we should take data on one flock under an external field, but then we really need to know whether it scales with the size of the system. So we should take data over many flocks with different sizes under perturbation. Yeah, good luck with that. Before doing anything of that anyway, we should get some postdoc in the experiment, which we are not doing now. We're not finding any postdocs. So this is not, if you want to do an experimental postdoc in our group, just apply now. So then we can go on the roof and try to do the experiment that the gentleman here is suggesting. So we don't know, but it should be like you say. Probably easier than that, it will be getting data on migrating birds. So migrating birds are not just going anywhere, they're going in one direction, right? Because they are going south, let's say, okay? So in that case, yes, really, I would not expect to get to obtain long-range correlation of the orientations, but we don't have data on that.
Thank you very much.
All right. There was another question. Okay.
There is the guy with the blue shirt. Yeah.
Yes. Coming.
So yesterday you said that the quasi-equilibrium approximation could not hold for swarms of insects. So can like the Goldstone picture can also hold for insects if the quasi-equilibrium approximation is not.
Well, no, I don't think it holds, but for a simple reason, it's not about equilibrium or not. In order to have Goldstone, you have to break the symmetry. That is, you have to have an overall non-zero order parameter. Swarms have zero order parameter. So swarms are much more, much closer to an Heisenberg ferromagnet at the critical point, or close, sorry, let's say close to the critical point, but above the critical point. So they're definitely not in the low temperature ordered phase. So in that case, you're not breaking a continuous symmetry, so you do not expect to have Goldstone modes. And indeed, the long-range correlation that one finds also in swarms, they need to be explained in some non-trivial way because you don't have Goldstone assisting you.
Okay, but we do see like some scale-free behavior in swarms as well.
Yes, we do find some scale-free behavior in swarms as well. Yes.
Thank you.
Other question? Yeah. All right.
So, hello.
Hello.
I would like to know, because all the computations we have been performing today, I think that we get the vectors just with 2 dimensions. So we have two coordinates, but the birds are flying in 3 dimensions. So I don't know how would this change the picture that we have.
No, look, it would be only very much difficult to do the drawing, but the algebra is exactly the same. If you are in 3 dimensions, then your Landau manifold is a sphere. Okay, so you have a sphere of ground states. And so the rotations are now rotations in a 3-dimensional space. And so you have 2 generators and 2 parameters, right? So you have 2 Goldstone modes in that case, right? And 1 longitudinal modes. So the algebra is exactly the same, but delta phi perp would be now a vector with 2 components. Would be the tangent, would be the vector, the field, the fluctuation spanning the tangent space to the sphere of the Landau states. That would be much harder to write the Mexican hat in 3 dimensions. That's it. No, it's exactly the same. It's exactly the same. Well, of course, Goldstone theorem, it's basically a group theory result. So things change with the dimension. You have to be careful, the abelian, non-abelian, and so on, but it doesn't change. So nothing that of what I did today was specific to a 2-dimensional field.
Okay, thank you.
All right. Other questions? No, that's it for today. So thank you, Andrea. So I think it worked much better than yesterday.
Yeah,
It wasn't difficult.
okay.
All right. See you,
Bye-bye.
see you tomorrow.
See
Bye-bye.
you tomorrow. Bye-bye.
Volevo dire una cosa.
Le cose, dilla.
No, sono tutti alzati.
Ma per la vela?
Per la vera
E
che
le
ci
magliette?
danno i soldi a mezzogiorno.
Ah, ok.
Ormai.
Per la vela, oh sorry, for selling, we collect money